This is Mr. Martin. These are the video notes for Geometry Honors, section 12.5. We're going to be talking about the volume of pyramids and cones. So much like we had with prisms and cylinders, the volume of any pyramid or cone is simply going to be 1/3 the area of the base times the height. So we'll normally write it as 1/3 capital B times H, where capital B is the area of the base. And then keep in mind that the area of the base can be any figure. It could be a circle, it could be a square, it could be a regular polygon. So keep that in mind, and we'll practice with that in the examples in a little bit. So another thing that we want to talk about in this section is cross-section of pyramids or cones. So if we take a cone and we cut it, we're going to get a cross-section here, either on the bottom part, which would be the top of our frustum, or on the top part. So we get this shaded cross-sectional area, and there's a relationship between that cross-sectional area and the area of the base. So we're going to use this weird symbol here for cross-section. I think the book actually just uses something that looks like a cent sign, but either way, whatever you want to use. So the ratio of the cross-sectional area to the area of the base is going to be the ratio of k to h squared, where k and h really are any corresponding parts. So k could be the radius of the cross-section, h could be the radius of the base, or k could be the height of the cone, and then h could be the height of the small cone, and then h could be the height of the whole large cone. So these really are just corresponding pieces of the two cones or pyramids. So in general, for any pair of similar solids, keep in mind this is really important, it's only for similar solids, that the ratio of the volumes is going to be the same as the ratio of any pair of sides cubed, and then the ratio of the areas, which would be the surface areas, is going to be the ratio of any pair of corresponding parts squared. And we've had this before with similar figures. So then S1 and S2 are any pair of corresponding parts. So keep that in mind. And we'll use that in an example as well. So moving on to the examples. For number 1, we've got a pyramid, and we know that the volume is going to be 1/3 area of the base times the height. So we need to find the height here, and we see this is going to be a right triangle in here. And you can either use Pythagorean theorem, or since I know that this side here has to be 11, I know that the height has to be 60. This is one of my triples. So that's going to be 11, 60, 61 triple. Again, you can just use Pythagorean theorem to find that out as well. So then we have that the volume is going to be 1/3. The area of the base is going to be 22 squared because it's a square. And then the height we've just figured out was 60. And if you calculate this out, you should get 9,680. And our units for volume are going to be units cubed. So if the units are included in the problem, make sure you include them in the answer. Moving on to number 2. We're going to make some assumptions about this picture here. Normally on a quiz or a test I'd make sure that these were very clear, but we're going to assume that this is an equilateral triangular base. And we're also going to assume that this slant height here is also perpendicular to the base here. Alright, so if I draw in from the center perpendicular to a side, that's going to be perpendicular there as well. So this side here is kind of straight up and down, and that's why we're going to use 16 as the height. So again, we've got the volume is 1/3 area of the base times the height. So it's going to be 1/3. The area of the base is going to be 8 squared root 3 over 4. And then the height is going to be 16. And if we simplify this, we're going to get 256 root 3 over 3 units cubed. Alright, pause the video when you need to, And if you have questions, make sure you write them down so you don't forget to ask me. Alright, moving on to example 3. Since we have a cone, the volume is going to be 1/3 area of the base times the height. The base is a circle. We know this is going to be 9. R is equal to 9. It's a 9, 40, 41 triple. So we've got 1/3 times pi times 9 squared times the height, which is 40. And simplifying this, you should get 1080 pi units cubed. Alright, last example up here, we've got that the volume is equal to 1/3 area of the base times the height. And again, we have a base of a circle, so that's going to be 1/3 times pi. Radius is going to be 6 squared. The height is going to be 5. And this gives us 60 pi units cubed. So for examples 2 and 4, the vertex at the top was not directly above the center of the base. Most of our examples will, so this was not right above the center, but it's right above that midpoint of the edge of the base there. But most of them will be more like examples 1 and 3. Alright, moving on to example 5, we want to find the ratio and the ratio of the areas and the ratio of the volumes of the small cone to the large cone. So we're going to use the theorem that we just talked about. So the surface area of the small cone to the surface area of the large cone. Since we know the heights of the cones, we can use those corresponding parts to find these ratios. So surface area is going to be the parts squared, so it's going to be 5 squared, and then the height of the whole cone is going to be 11, so that's to 11 squared, and that's 25 to 121. We really don't have enough information to find the actual surface areas and volumes, but since we have these corresponding pieces, the heights, we could do it that way. And then the volume of the small cone to the volume of the large cone is going to be 5 cubed to 11 cubed, or 125 to 1331. So if you have any questions, again, make sure you ask, and that's it for this section.